Dear students, welcome to another lecture of Statistical Physics 1. The theme of today's lecture would be equations of state. We will revise some basic concepts in thermodynamics, and later we will see how our understanding can be improved about this subject. So let's begin. So thermodynamic quantities that we studied in the last lecture were internal energy, that we defined that if a system is not moving, the energy contained in that system is called the internal energy. We will usually denote it with U, or sometimes we can denote it with the sign or symbol E. Temperature, we said that it is a measure of internal energy, and you know it from your previous knowledge that it is an average kinetic energy of the system. You remember it from your previous knowledge. And heat is the is a mechanism or a way in which internal energy is exchanged between two systems besides work, in addition to the work done. So continuing in the same fashion, last time we looked at the laws of thermodynamics. The first law says that the total energy of a system is conserved. So total energy can be in the shape of heat added to the system or work done on the system. So the sum of these two remains constant. This negative sign is due to the sign convention, but overall result is that energy of the system is conserved. So next we see how we can compute the work done by a system or a gas on its environment. So if you recall your or refresh your knowledge, so imagine that we have a system consisting of a gas cylinder fitted with a movable piston that we can move its position up and down. So initially the piston was at some position Vi of the volume, and we reduced pressure on it, so it changed its position to some final position Vf. So in this case the work done by the gas, because the gas is expanding, the gas expands. So please remember that this is an ideal situation. So the piston moves from Vi to Vf. So normally in mechanics we used to calculate the fractional amount of work done with the formula that work done is equal to the force times the displacement. Okay, this is the basic formula that you know from your FSC or even metric books. And now we just do some manipulation to this formula. So we divide and multiply this formula with area. What do you call it? Area of the piston. I would say this is area of the piston. Or surface area of the piston, whatever you call it. And you just multiply and divide with this formula with A. And now if you see that if the piston has moved ds distance along this axis, whatever direction you call this, so it's moving a distance ds. So the product A times ds is actually dv. So it adds the third dimension to it, so it's the volume. So and dw is the change in volume. So we just replace A times ds with dv. So now and another change is the definition of pressure. So pressure is defined as force per unit area. So we replace 4 per unit area with P and AdS with dV. So we get work done in thermodynamics, or what you call this macroscopic work done, we call it in thermodynamics. So dW is the fractional work done when there is no change in pressure. So although we have reduced the pressure, but we are not counting on that. So we are just seeing what is happening to the volume. So in actual, both of the quantities do change. Pressure also changes. So there is a quantity dPV and there is a quantity PdV, but we are only considering the slightest work done, that is that has been accomplished with just change in volume. And if we now want to calculate, suppose we have had a bigger cylinder, so a very large cylinder, for example this of this size, and we just calculated the work done when the piston moved from this position to this position initially. So it changed from this position Vi to this position Vf, but in actual it's not the final position, so we call this not Vf, but we call it as Vi2. So it moved from Vi1 to Vi2, but we want to calculate the work done, total work done, when it would have reached at this position, and we call this position as Vf. So there will be a lot of intermediate steps in this area of the cylinder, and to calculate the complete work done we have to integrate this equation that I showed you on the slide. So we have to integrate this equation to get this complete amount of work done, and the limits of integration will be from Vi to Vf times Pdv, and it will be it is basically sum in the beginning of large number of steps, and then when the step size is very small, then we can change the summation to integration. And this is the work done that we will now onwards be using for our thermodynamic situations. So whenever we will encounter a work done in a gas cylinder system, so we will use this kind of notation, and remember that in this notation the pressure is not changing, so pressure is P is constant in this case. Okay, so let's move a bit forward, and we can see different situations in which work done by a gas can be calculated via graph. So on a graph, you see there are two axes. On one axis there is volume, and on the other axis there is pressure. X-axis volume, y-axis pressure, and you have seen that work done is actually the product of pressure and volume. So area under the curve will give us work done. So for example, consider the situation A. So in situation A, we see that the volume changes from point I to point F, and we see that the area under the curve is this orange, this area highlighted with the orange, and this work done, since the volume has increased this much amount, so the work done is positive. P delta V is positive. Again, we see in the second graph number B, we see that this time initially the pressure remains constant. So in first case you have seen that pressure has decreased but volume increased, but in second case the pressure has remained constant for some time in the beginning, and then pressure drastically reduced after point A, and it went from A to F. So again, so the area under the curve is only due to the part of the curve between I and A, so it will constitute only the work done. And again, since the volume has increased, so work done is again a positive number for this situation. So this number C shows another similar situation in which in the beginning the pressure has decreased, but the situation was such that the volume did not change from point I to some point, okay, whatever we call this point, I to J. So in the beginning nothing happened to the gas volume, although we have decreased the pressure. But all of a sudden, when it reached point J, when pressure remained constant, but volume increased from point J to point F. So again, there is some work done, and this work done again is given by this shaded area. And these are the three typical situations. So you can be asked in exam, for example, to calculate some work done in a similar situation. But you know, these work done were in some specific direction. There will be some cases when this work done is not in a specific direction, but somehow in a closed path or something similar, and we will see how to deal with those kind of situations. We see another situation here in pressure volume work done, where we start from point I. The pressure keeps on decreasing till point C. At point C, then it takes another route, and then the volume keeps on increasing and it reaches point D. And at point D, again we increase the pressure, but volume does not change, and we reach at point H. Okay, so in this case, so there have been two routes that have been adopted. So from I to D in one direction, and then from I to D, I to F from another direction. So in both cases, if you see that work done is different. So in case when we are moving along this reddish kind of line, so only area under the curve is this area. I highlight it with some different colors. So this is the area that is under the curve for if we move from point I to point F via this route. And if we take another route, that is if we go from I to G and then G to H and F, we see now in this case the area under the curve is very large. So this is the area in that case, huge area. So it shows that the work done is path dependent. Work done in thermodynamics is a path dependent phenomenon. So if you change the path, the amount of work done changes. So we take another case now. So the other case is we start from point F here in graph E, and we move from point F to point I, and here we are decreasing the volume of the gas, although pressure is increased, but overall work done is negative. And again the work done is the area under the curve. Although the work done is negative, but still we can calculate it by calculating the area under the curve. And last, in the graph F, we have a very interesting situation. Here we see that we are doing work in a closed path on the PV diagram. So if you see that initially we move from I to F, and then we move back from F to I, and our understanding about conservation of conservative fields. So we usually have seen that in those cases the work done was zero, but in case of thermodynamics it's a totally different case, because the work done is a path dependent property, so it's not a conservative kind of thing. And in this case, when we are doing work in a closed path, the work done is actually the in a closed path the work done is the area enclosed by the path, by the closed path. So the area, if we have done work only from I to F, there would be a large amount of work done. That would be the bigger area under the curve. Or even if we have done work only from F to I in this direction, then still the work done would be larger. But if we have done work in such a fashion that we have moved from I to F and then F to I, then the area enclosed by the path gives the work done only. So this is the small introduction about the pressure volume work done in thermodynamics, and we see later I am giving you examples that there are other kinds of work in thermodynamics that we may discuss later. So these are called configurational works. So not called works but configurational work only. And in this case, so for gases, liquids and solids, we are using the work done PdV that we have already seen, this first term. And if we have some magnetic material which when we apply magnetic field B, and as a result of it we get some magnetization, so in that case there is also some kind of work done. We call it magnetic work done, and this is given by B times dm. Dm is the change in magnetization. So we may come across some examples which will deal these kinds of work done. And the third type is the dielectric work done, and that is given by electric field. E is the electric field times dp. dp is the change in polarization. So we apply electric field, and it may happen that there is a dielectric material which has some permanent dipole moment which is disturbed, permanent zero dielectric constant which is disturbed, and then that kind of work done will also be considered sometimes. We may or may not consider some examples, but they do exist in thermodynamics: PdV, BdM, and EdP kind of work done. So remember that these are not these are only two terms: pressure and change in volume, magnetic field and change in magnetization, and electric field and change in polarization. You should not read this as three letters. There are only two variables in these equations. So you need to somehow know that these kinds of work may exist. Now we discussed equation of state for a gas, for ideal gases, I would say, for ideal gases. So you know that this is derived from the basic gas laws, this Boyle's law and Charles law. So pressure is inversely proportional to volume, and pressure volume is directly proportional to temperature, and when we combine these two, and there is another, that is pressure volume is directly proportional to the number of moles. But okay, this is the ideal gas law, which shows that pressure volume product is equal to the number of moles. N is the number of moles, V is the volume, P is the pressure, R is the universal gas constant that has a value of 8.31 joule per Kelvin per mole, and T is temperature in Kelvin scale. This ideal gas law you have already known very well, and you have calculated certain values. For example, sometimes you are given PV product and you are asked to calculate temperature or number of moles or something like that. So you are familiar with this ideal gas equation, and this is called equation of state for ideal gases in our thermodynamics terminology. And if we now want to introduce some other quantities like molar volume or something like that, in where we can divide this n on the left hand side and we get molar volume, but we will not use this equation so often, so let's leave it as such. Okay, so now I want to discuss with you a little bit about the phase diagrams. So phase diagram is something that gives you information about the state of that particular material on under different conditions of pressure and temperature or volume and temperature. So we have on one axis we have pressure, and on the other axis we have temperature, and sometimes we have volume and temperature, and sometimes we have pressure and temperature. And these curves that you see here in this graph, they give you the state of that particular material. It can be anything: water, some metal, some other compound. And the phase diagrams tell you that at which condition of temperature and pressure which kind of material that exists. So in this figure that you are looking at now, so it is there are two different kinds of materials. One material which is shown in the part A, this substance when it is cooled down, its size reduces, so it shrinks, and this is the general definition. And then on the right hand side, the phase diagrams correspond to a material or a substance that expands on freezing. And now we see what these lines mean. So I somehow tell you in more detail what these phase diagrams show. So we start with some point. So let's start beginning from here. So on this side of material, this side of this phase diagram, when we have a pressure, some low pressure, so you see pressure is increasing in this direction, and temperature is increasing in this direction. So if we are somewhere here, I just show you what I want to say. So if we are in this region, so we are in the low pressure region. This is the low pressure, low P region. And what this phase diagram shows that this particular substance, I have not told you which substance is that. You should find out by yourself, but we are discussing its characteristics. So in the low pressure and low temperature, so temperature is also low in this region, so I just draw another line to show that which region is the low temperature region. So in this region now, which I highlight with this ink, this region, so you see there is a line, and the line shows that on this side the material is in vapor state, and on this side it is in solid state. It has been written before. So there is a line in between them. This line shows that whenever we have a pressure and volume, a combination of pressure and volume that constitutes this point, this small dot, the material will be a vapor, in a vapor state. It will be vaporized. As soon as we increase a pressure little bit, keeping the material on the same temperature, the material will become solid. This is so interesting to see. So here it was vapor, and as soon as we increase the pressure a little bit, it became in this direction it became solid. And this line is a line of coexistence. Actually, it shows that if we have a combination of temperature and pressure we that exists really on this line, so then we are on the coexistence line. So this line is a coexistence line, or a boundary between solid and a vapor. And now we discuss what happens when we increase the pressure and keep the temperature somehow still low. So now we increase temperature a little bit, so we are moving from this pressure to, we call this pressure P1, and let's move to this pressure, this temperature, I am writing temperature pressure. So we were temperature at T1, and now we have moved to temperature T2, and I am drawing a line corresponding to it. So, and we are keeping temperature still a bit low, but we are increasing the pressure. So now we are in this region, for example, in this region. In this region, if for example we have some pressure and some combination of pressure and temperature, that this is the point where our material is located. So this material is located at low pressure and low temperature at solid, high pressure and low temperature in solid state. And if we now increase the temperature slightly higher, we go to liquid state. We go to liquid state of that material. And the line now, this line that is from this point to this point, this line is called the solid liquid coexistence line. So any point on this line means that there are both phases coexisting. So the material is simultaneously liquid and also solid. And on either side of this line we are either liquid, or on this side we are solid. And this is also called the when we convert from solid to liquid, what we call this phenomena, we call this melting. So this can also be called a melting line of temperature and pressure phase diagram. This would be a sublimation line. What we call this? We call this a sublimation line. And we call this line as freezing line, or melting line. Freezing or melting, whatever you want to call it, is more or less the same. This whole line, starting from this point, which is marked as TP or triple point. I will get to that triple point in a while. In a short time, I will discuss about triple point. So there is a third line that you see here that starts from a triple point and moves in this direction. So on either side of this line, so here we have vapor, and on this side we have liquid. And this is what you call liquid vapor coexistence line, or what you call boiling line. So when you convert a liquid to a vapor, we call this boiling phenomenon. And you know that this happens at larger temperature. So here the temperature is increasing, so there is a point at every combination. So here there is another interesting thing to see from your daily observations, that when you are heating water in your houses, for example, if you are living in Lahore, and then water may be boiling at 100 degrees C or maybe 98 degrees C, so it boils. So that combination of temperature or pressure would be somewhere, say let's suppose it is somewhere here where I have drawn a cross. And now imagine you are moving to some hilly area like Murray or in northern areas where the pressure is reduced. You see what I mean? In areas, in hilly areas where uh, pressure of air is low. So there we see that if you there try to boil water, it boils at lower temperatures. So now if you see on this curve, you are somewhere here, you are in lower pressure region. So this was higher pressure region and this is the lower pressure region. So your temperature, boiling temperature, is also reduced, and this is also kind of phenomena that you observe in daily life. So this phase diagram has been established with the help of several experiments of that particular liquid. I don't know which liquid is that, but this is a liquid which contracts on freezing. It can be water also. You should determine. You should search Google and tell me what to which substance this phase diagram corresponds. Okay, so we are seeing that at low temperatures and high pressures, the substance may be solid, and this solid phase exists even till low temperatures, and then there is a solid vapor phase diagram, that the material is converted into vapor state, and when we increase temperature, it becomes vapor rather easily. And there is another phase that exists in this material, that is a liquid phase. So the solid phase, you can imagine that this is ice, this is like liquid water, and this is the vapors, water vapors that we see in air. So and these are the crossing lines depending upon the particular values of pressure and temperature. Another similar okay, so let me discuss triple point first. So when you join these three lines, this solid vapor, liquid solid, and vapor liquid coexistence lines, they join at a single point, and this single point is called as triple point. And at triple point, this is really like a amazing phenomena, that all three phases coexist, but this is only one combination of temperature and pressure. So this is only one combination of temperature and pressure, where all these phases coexist. So at this point, really at the middle point of this shaded red area, that there is also liquid water. If this is water, so this is liquid water, this is there is also ice, and there are also vapor at that particular pressure and temperature values. So my question to you is, you should research a bit and tell me what is the triple point of water. So you should tell me, your assignment is that you should tell me, you should research what is the triple point values of water. I should not call it water, but I should call it H2O. This is more scientific way to say that, because water means normally solid water, liquid water. So another particular assignment that I want to ask about this graph is, tell me where on this graph it shows that this substance contracts on freezing. Where on this phase diagram it does show that this substance contracts on freezing, like its size shrinks. And also you should tell me at which point on this phase diagram this it shows that this substance expands at freezing or on freezing. More or less the phase diagrams, there is no different explanation for that. So there are solid liquid phase crossings, liquid vapor phase crossings, and solid vapor phase crossing, and there is a triple point, and there is another something that we call at critical point. And at critical point, what happens is that there is if you go beyond this critical point, so you see that if you now increase pressure in this direction or you decrease pressure in this direction, you don't see a phase change. So there exists no phase distinction between two phases if you cross the critical point, and this critical point only exists at liquid vapor coexistence line and not on the solid liquid coexistence line. So this exists only on liquid vapor coexistence line, that after a certain point that we know as critical point, there is no distinction between a liquid phase and a vapor phase, whether you increase pressure or decrease pressure or whatever. And that is it for today's lecture. I hope you have understood some things related to basic thermodynamics, and we meet again for the next lecture discovering van der Waals equation of state. Till then, I would say bye bye.